So let's look in a little more detail exactly how's this luminosity produced and how's that energy actually released out. And the first thing that is important to know is that it's probably the mergers of gas-rich galaxies that are fueling a lot of the, at least spectacular, quasar activity. It doesn't have to be always a merger. For example, a Seyfert galaxy can be a spiral disk, normal spiral otherwise. It's just enough interstellar medium that flows to the middle to fuel the active nucleus. But you may remember when we talked about galaxy simulation, merger simulations, that stars do their thing, but gas loses energy much more efficiently because of dissipative processes. Gas clouds collide, and gas sinks to the middle, much more so than stars. Well, it can make a very dense blob, and if there is a black hole to be fed, that can provide perfect fuel for a very luminous episode. And so we think that actually quasars are not always on. They last maybe some tens of millions of years during one of these merging events, and then there'll be another one later on. And so there is a lot of circumstantial evidence from pictures of quasar-host galaxies like these from Hubble Space Telescope that show that there looks like some of the dynamical interactions that we see. So in fact, accretion is the only plausible way we have to power objects that are this luminous. And the material comes from sufficiently large radius, so compared to binding energy right near the black hole, its binding energy at start is essentially zero. And so if you go from tens of kiloparsecs down to microparsecs, you can in principle get rid of all of the binding energy, all of the MC squared can be turned into luminosity. Now that doesn't really happen. If you could do it directly to the Schwarzschild radius, you could really radiate away 100% of the rest mass energy. But in fact, no, they settle into the accretion disk, and the accretion disk has an inner edge, which is the smallest stable orbit. Now, this is where the differences between Einstein gravity and Newtonian gravity come in, that for Newtonian gravity, there is no such thing as the smallest possible orbit. If you have point masses, you can put them as close together as you wish. This is not the case in general relativity. So there is a smallest possible orbit, and its radius is several times Schwarzschild radius, and it's different for spinning black holes and for stationary black holes. It's closer in for spinning black holes, which means larger amount of rest mass energy can be radiated away by a spinning black hole. And so that's efficiency factor, which is maybe a few percent on average, and so a few percent of the rest mass energy of the infalling material gets turned into radiation. Now, how luminous can you make them? Well, remember Eddington luminosity, which is the limit of the stellar luminosity. This is the luminosity at which the radiation pressure balances gravitational pull of the star. And if you have more radiation pressure, it'll blow envelopes away. And so that's what sets the upper limit to the mass of stars. Now, there is no upper limit to the mass of black holes, but it tells you that for a given mass black hole, there is the maximum luminosity it can have if it's accreting isotropically. And that's the Eddington ratio. So now we think that, in fact, most of the active nuclei, when they're on, they're accreting at nearly Eddington rate, as fast as they can. And if you ask, well, how much accretion do you need to produce these luminosities that we see? Well, the answer is you need millions to hundreds of millions of solar masses. And that's, in fact, the kind of masses that we infer from dynamical measurements. So it all kind of makes good sense. Now, because Eddington luminosity is proportional to the accretion rate, it's also proportional to the mass itself. This is going to be an exponential process because the bigger black hole you make, larger Eddington luminosity you can have, the larger accretion rate you can have. And so in principle, if you don't put any brakes on it, black holes will grow exponentially and get exponentially more luminous. Now, that doesn't happen because at some point they run out of fuel But whenever they do happen, that seems to be the case. And so where does this energy actually come from? Well, a lot of it comes from just thermal energy in the accretion disk. That material has now releasing so much binding energy that it's very, very hot, and temperatures of inside accretion disks can be millions or even tens of millions of degrees close in, less as you go further out. So the emission is a combination of many, many black bodies of different temperature. In addition to that, if you're accelerating electrons with magnetic fields, they're going to emit synchrotron radiation, which you may recall from the early parts of the class. And usually, the distribution of energies of electrons, it tends to be a power law, which also then tells you that the spectrum of the emerging radiation will be a power law. It'll go frequency to some power. Minus alpha typically goes as minus first power of frequency or something like that. Not through entire range. At very high energies, you get a cutoff because electrons are losing energy so rapidly. At low energies, you get a cutoff also because those same electrons can then absorb energy emitted by the little faster electrons. But say in radio regime, or sometimes all the way to X-ray regime, you can have something that is close to power law. So this is a non-thermal emission, unlike black body, and the overall emission from quasars is a combination of these components. So here is the spectrum, average spectrum of a quasar in the optical and ultraviolet, and this is now, and in fact, if you draw a line through it, you can see that this on a log-log plot, that it's a straight line, it describes continuum, so it's a power law continuum, at top of which there's some bumps, which may be thermal emission, plus the emission lines. And the cutoff in the ultraviolet is due to the gas between you and the engine. So this explains this plot that I've shown you earlier, why there is such a broad and nearly flat, but not exactly flat distribution of power emitted per log frequency interval versus frequency. So it's kind of flat, and there are bumps on it, and those bumps are thermal emission. There is thermal emission from the accretion disk, that's called the big blue bump. There is also thermal emission from the dust around the whole thing, that's called the big red bump. And in radio, it's just a synchrotron emission from the electrons. In X-rays, it's mostly synchrotron emission from electrons, but at very high energies. So what about those jets? This is the cartoon version of what happens. You have magnetic field that's threaded through the accretion disk because it was frozen in the plasma that collapsed down, or maybe even inside plasma that fell into black hole. Because it's a long-range interaction, you could have magnetic lines of force go through the black hole. And it gets wound up by the spin, meaning field strength goes way up, and acts just like an accelerator, accelerating electrons along those lines. So this has been observed mostly in the radio, and those jets are persistent over very large scales in radii. Now what's shown here is map of M87, active galaxy in Virgo cluster. And if you zoom in from a very large scale to a smaller scale, and zoom in and zoom in and zoom in, you always see that there is always a jet from a central source pointing in one direction. So radio jets are very common. The reason why they're so persistent is that, well, particles are moving at almost speed of light, so they will carry on a linear momentum, right? And in case of M87 and some others, they also shine invisible light and X-rays as well. They're not uniform, they're little blobs, and we can actually see them move with observation spaced in time. So that is now very commonly seen everywhere, and there is one of the nearby active galaxies where you can actually see the obscuring torus superposed on an elliptical galaxy, and there is a point source in the middle, and radio jets that come out are orthogonal to the torus. So the whole picture makes a lot of sense. Now, in 1970s, people noticed something else fun, that you can see sometimes distinct blobs, and they're moving out, just globs of plasma that have been accelerated out. And they found out that oftentimes they move faster than the speed of light. And that was kind of a problem, right? And so what was finally realized is that this is not real. This is an optical illusion that's specific to relativistic motions, that clocks tick slower over there. And under the right projections, things will look like they're moving faster than the speed of light to you, but over there, they're just under the speed of light. And people here at Caltech have played an important role, Tony Reed and Marshall Coyne, and Roger Blandford in understanding how this happens. Now, we've seen the same thing happen in what we call microquasars, which are the little black hole binaries inside the Milky Way that operate pretty much in the same way, only on scales of millions of times smaller. So that's what they call superluminal expansion. Material is not really moving faster than the speed of light. It just, projection looks like it's moving faster than the speed of light.